Alright, our last video we have 1.4 standard, so we're doing those regression models. First thing to note when we do these, we can do them either via Desmos or our graphing calculators, but on this video I'm just going to use Desmos to demonstrate that. So when we look at these problems, the first thing we need to do is get these plotted into a scatter plot, and to do that we go to Desmos, and here they are. So I've already inputted the data, and what you'll note right away is you can't really see much because it's zoomed in too far, so you always want to just go down to that little magnifying plus, and there it is. So when we answer these questions, it says, part A, find a regression model. Well, I know at the beginning of the unit, or this section, I emphasized use the highest R-squared value, but we're at a point now where we can really start to hone in on what is the real world application being used here. And I'll just come out and tell you, if you don't know this, or if you didn't hear me say it in class, that anytime we have a bouncing basketball, softball, baseball, whatever it is, if we have a ball being thrown or a ball dropping and bouncing, every one of those is based on a quadratic regression. It has to do with the fact that gravity is the only thing pulling it down, and gravity is constant. So with that said, we could go through and check other regression models here, but because we know it's a bouncing ball using gravity, I'm going to come out and say we're just going to use quadratic. So here it is. Again, these equations for the general forms will be available to you. You don't have to have them memorized, but you would type that in and it gives you the R-squared value. It also gives you those coefficients. So here's our best case scenario. That's approximately where the ball is at any given time. So part A is asking for two things. It's saying what regression model, and I'm telling you it's quadratic, but is also really implying, and on the test it's very clear, that it wants to know the equation itself. So that's where we don't need to write all of the numbers in here. We can round some of this. So negative 0.1179 x squared plus 2.112x, and then plus there you go. So that's really what A is asking. Now in B, we're going to be asked to apply that equation for another point of data that we don't have numbers for. So here it's saying, what is the approximate max height? In that case, we take our graph, and actually if you look at it, Desmos is really kind to us, and it's like, hey, you're probably going to want to know this peak at some point, so here it is. So what we're doing with this information is knowing the xy, we can't just put this coordinate as our answer. We need to interpret the information, and the y value is our height, right? Because that's from our table over here. X was the time and y was the height. So what we know is the maximum height was 13.675 feet. So the answer is like I said time previously, the x column is just the distance you were at when you dropped the ball. So, or shot the ball for the free throw. We've answered the question. There's a max height. We can move on. Number 16. 16, again, we can plot the data. In fact, that's the first thing we want to do, is go over here and plot our data. Also, again, negative 10 to 10, so that's not very helpful. We go over here and we hit the zoom right here, and we get the data. As I look at this, I look at that and see, I don't find too much of a curve. It looks pretty straight to me. Even though it's scattered, I would call that linear. But so you can run through these and look at your R-squared values, and when they're that close, 936, 9396, 9328, what you're really finding is that there's nothing that stands out as obviously right or obviously wrong. So then what you need to do is look at the problem at hand. And the problem is about femur length and the height of the person. And think about the common sense approach here. if the person is small versus a person's larger, does that really mean that our data would be exponential? Like the taller you are, then exponentially your bones will be longer, right? Like that doesn't really seem to make sense. So from that regard, from the common sense approach, this data would be linear, because it's not like shorter people have exponentially smaller bones, right? Or taller people have exponentially larger bones, or anything like that, quadratic. So we are going to use that linear approach. We're going to type that in. And yeah, it's not a great R value, but it's the best we can do. So we're going to type that in as our answer. 1923. So I'm going to say linear. Y equals 1.923x. 1.923x plus 86 plus. And there you go, that's the answer to A. Now, B is saying an anthropologist finds a femur of length 58 centimeters. They're asking how tall the person was. So we don't have 58 on our chart, so we need to interpret that. And it is well within or close to our data we have. So let's look at that graph for 58. So two ways to do that. You can click and drag until you get to 58. In fact, let's zoom out. And when we get to 58, again, you can, it's kind of tedious to do this, and you get close, 58.03, and then all of a sudden you're short. So that's one way to do it. The other easy way to do that would be that we know that we're looking for when x equals 58. Okay, then we hit enter. Now we have a line here, and what we can do is we can click over here, and it tells you exactly, there it is. So here's our x is 58, the femur length is 58, the height of the person is 192.82. So we say that anthropologists that how tall, they were 192.22 centimeters tall. We box that in. So that's how you go about doing these regressions. You put in the data in the table, you use the little zoom key, you run through the simulations of the regressions and find the best fit. Typically, we're going to be able to find a real-world scenario of that, knowing what the data should do, and we apply that. If we can't, that's when we go to the R squared or R value. Whichever regression has the highest, we would go with that. So hopefully that made sense, and that is the end of our review. The answers are down here, so we don't need those. I appreciate you listening. We'll see you in the test.